Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And within that playlist, we do little mini-series on the different types of experimental designs. And this one, we're doing one on analysis of covariance. And we're on part 8 of a 9-part series. And this is an R illustration of analysis of covariance. Specifically, it's a one-way fixed effects ANOVA with one covariate. Now, the example is taken from a book by Montgomery. It's 17-1. And let's just jump right in. And so I always like to remove all objects first. That way there's no duplicates. Y is our response variable, machine, and diameter. I actually forget what the example's about, but it's from Montgomery. So let's load the data. And in part 1 of this mini series, we do what's called model development. And so we're going to take this. Well, let's look at the data first. So Montgomery, here's the data. So we have our response, our machine, which is like a treatment 1, 2, and 3, and diameter is the covariance associated with it. Now it's in a data frame, but we're going to put them in individual variables. So Y is going to be the response. We're going to have a vector of ones. We're going to have a matrix that deals with the treatment effect, and then the covariance. And the design matrix looks like this. So we have a vector of ones associated with the mu parameter, x tau, so these are associated with the treatment effects. And then this is the centered covariance. Notice that this is our original data, but then we subtract the mean from each of those, and it's called a centered variable. Now in part 2, we look at the different column spaces of the design matrix, and it's kind of a neat little video. We add a well-chosen 0, and then we kind of manipulate the model. It's 100% the same, 100% the same column space, but we do it in a way that we can develop structure for our least squares estimates. So in this, we need the mass library, because there we can grab access or get access to the generalized inverse function, and that's what this first one does. So M is a generalized inverse onto X, the whole column space, and that's what it produced. And we're going to need several of these perpendicular projection matrices when we get into F testing, so we'll just run them all here. Now M.Z is going to be the perpendicular projection matrix onto the column space of Z, so it's Z times Z transpose Z inverse times Z transpose. Now MT, which stands for M tau, it's the perpendicular projection matrix on the column space of X tau. J is the perpendicular projection matrix on the column space of ones. ID is the identity matrix. Capital I is like a reserved function in R, so I can't use that, so I use ID for the identity. MIZ, if you were to go to part 2, where we talk about the column spaces of the design matrix, that's where we manipulate it. And part of the column space is the identity matrix times M tau times Z. And then that's the column space. It actually ends up being orthogonal to X tau. But we need the perpendicular projection matrix onto that. So that I'm going to call it MIZ, because there's an I and a Z. And there we showed that M, the perpendicular projection matrix on the column space of X, is actually equal to the addition of these two perpendicular projection matrices, M tau and MIZ. And when we use the all equal function, it's true. And then we're going to need one more perpendicular projection matrix, and this is where we remove any parameters associated with the treatment effect. So we have a column of ones, and then Z, where and X tau has been removed. We'll need this perpendicular projection matrix when we do F tests. Now, deriving the least squares estimates, I actually think this little subsection within this program is pretty darn cool. In part 3, we derive the least squares estimates for the betas and the gammas. Now the betas are associated with the ANOVA model, and the gammas were associated with the covariates. So gamma tilde, since we only have one covariate, we have one gamma parameter, and the least squares estimate is gamma with a tilde above it, so I call it gamma tilde. And this is it. It's and I'm not going to say it, but you know, in part 3 we derive how it is, and notice it's 0.9535, and this is uniquely estimable because Z transpose I minus m tau Z is invertible. It's a 1-by-1 matrix, which is invertible, right? It's just 1 over that. So then we showed that it's uniquely identified, and it is 0.953. Now you'll see why that's pretty cool in a second. Now here I need a library called PRA-CMA, and in that it has what's called a null space. So I want to grab the null space of this column matrix, and I do that because it helps me create different generalized inverses matrices to create different least squares estimates for the betas. So this is a GI1 is the generalized inverse 1, and so we take the generalized inverse of X transpose X, and this next function shows that it is an inverse. So we take X transpose X, generalized inverse X transpose X, and that should equal just X transpose X. And it does. And we do the same thing. We add a vector from the null space. That's what I'm doing here to each column. And then that will help us create another generalized inverse. And this all equal shows that it is a generalized inverse. So now let's create two least squares estimates for the beta parameters. Now this beta parameter is for the whole model. So gamma is involved in it. It's actually the last parameter of this. So generalized inverse X transpose Y, generalized inverse 2 X transpose Y, and let's look at them and notice that they are quite different. Notice that the gamma parameters are the same, 0.9539877, and that's because the gamma parameter is uniquely estimable, but the parameters associated with the ANOVA part of the design matrix are not uniquely estimable. And gamma tilde, which we calculated up there, is the same. I just wanted to show that it is the same as that last parameter. And to me, that's kind of neat in itself to know that that gamma parameter is uniquely estimable, even though the other values are so different. But then we also showed that the least squares estimates are not unique, which they're not, right? You can tell here. But when you take X times that least squares estimate, that is unique. And so let's look at each of those. So we take X times that beta parameter, X times that beta parameter, and look, every value is the same. It's a unique estimate. Now in part 9, we look at the sum of squares errors. So let's look at these full models here, mod 1 and mod 2. Notice it's all the same variables, but they're in a little bit different order. So if we look at the ANOVA tables, and that's what you get with the summary function, the residuals are the same, 2799, 2799, but these sum of squares are different. And there's two reasons. One is the columns of our design matrix are not orthogonal. So we lose that nice property that all these sums of squares are the same no matter what order you put them in the model. Now, R calculates type 1 sums of squares. So these are all conditional on what terms are added before the model. And you can tell they're different. Now, the residuals is always the same. It's always I minus M, and where M is a perpendicular projection based on the column space effect. So it's Y transpose, I minus M, Y. And we better get 2799, and we do. Now the rank is the rank of that quadratic matrix in the middle, and that's 11, and the degrees of freedom is 11. So they are the same, and they better be the same. So let's look at another one, sum of squares treatment, and we're only looking at the diameter. So we're taking out the effects of the machines, and we're looking at this reduced model. So 305.13. Notice that that is the same as this, but not the same as this one up here. And these are the same because when type 1 sums of squares, that first variable added is, it would be the same. Residuals 4127. So the perpendicular let's look at this ANOVA. We're taking the difference between mod 3 and mod 2, and that calculates the reduction in the sum of squares there. So if you notice here, we have 4127, 4127, 27986, and that's what this is, 2799, but it just, here's the next decimal. There's 2 degrees of freedom associated, and the sum of squares is 13,284. Now this is the reduction in this. If you just take that difference between these sums of squared error, then you get that. But I'm saying that it's M, which is the perpendicular projection on the full model, minus M.1.z, which is the perpendicular projection on this reduced model. And then, of course, out front it's Y transpose, out back it's Y. And notice we get the same value, 1328, 1328. The degrees of freedom better be 2, and it is 2 and 2. Now let's do this. Let's run a reduced model with the covariance out of the model. So we just have the machine effects. And let's look at mod 4, which is this model, minus mod 2, which is the full model. And notice the sums of squared errors. We have 206, 206, and this 27986 was from the full model. That difference is 178, 1 degree of freedom. And notice here, so we have M, which is the perpendicular projection matrix on the full model, minus MT, which is the perpendicular projection on this reduced model. So if we look at that, it should be the same, 178.01, 178.01. The rank of that quadratic matrix is 1, and that's why the degrees of freedom are 1. Let's look at the mean squared errors and the F-test. So as a reminder, this is the full model, and I always do diameter first because that's the covariate, and then the sums of squares for machine is adjusted for diameter. And so this is an accurate estimate for what it is. The mean squared error is the sum of squared error divided by the rank of that quadratic matrix. So mean squared error is 2.54, and we got 2.54, so that's the mean squared error. Now mean squared treatment is this, which is 6.64, 6.64 under the mean squared error. The F value is the ratio of the mean squared treatment and mean squared error, and it's 2.61, which is exactly what we have here, 2.61. The p-value is the area in the right tail. Let's see. And it's 0.118, 0.118. So they're the same. And so this is how you calculate it from scratch, and I'm just showing you what these values in the ANOVA table equal. Now, estimability is so this is part 5, estimability. So individual parameters are not estimable in this analysis of covariance. We would use, so in this playlist, General Linear Models, Design of Experiments, I have a little mini series on estimability. It's a 4-part mini series, and it gives you a foolproof way to check to see if something is estimable. If you take your linear combination and take it times the generalized inverse of x transpose x times x transpose x, if you get this linear combination back, then it's estimable 100%. If you don't get it back, then it's not. It's an if and only if proof. So we're taking linear combinations of the beta parameter, beta vector, and 1 and then the rest 0, so that picks off the mu parameter. Let's see if it's estimable. And notice we don't get 1 and the rest 0, so it's not estimable. And we can do this for all the rest of the, if we just pick off tau 1, tau 2, tau 3, but notice this last one. That's for the gamma parameter, and it is uniquely estimable, which we can create linear combinations of it. In this case, there's only one, so it's sort of silly, but notice we get the vector back. So it's estimable, and that's uniquely estimable. So that's kind of cool. So linear combinations are estimable. So this is the treatment 1 effect, not adjusting for the covariate, and it is estimable, right? Because we get it back. And then the same way for the others. Now these next combinations. So this is linear treatment effect for machine 1, adjusting for the covariate, and then it's the same for the others. So we do get them back when we use that theorem in the part 4 in the mini series on estimability. So now I want to show you that using these different least squares estimates for beta, but the same linear combinations, estimable means that we get a unique estimate if we use those linear combinations. So one of the linear combinations that we set up here was unique, was this. So that's a linear combination times beta 1, the least squares estimate, beta 1. And this is the second least squares estimate. Notice that the linear combinations are 100% the same. And that's and if that's, they're estimable. That's why they're the same. And if we pick another linear combination that creates an estimable function, we get the same. Here we're creating treatment effects between the first and third treatment, and the linear combination is the same. The variance of these estimates are the mean squared error, and then times those. In theorem 1, we state that if we take a linear combination of the parameters for the ANOVA design, then it's estimable if it equals a certain function. And that's what we're doing here. So P1, I kind of find out what linear combination of the row space we need for this to be estimable. And then theorem 1, and I'm going to point you that and not talk much more about it here because it's already running long. And we get our linear combination back. And theorem 1 tells us, well, we better. Theorem 2 says if it's estimable, and then if the linear combination of the beta parameters of the treatment parameters, so the tau parameters by themselves, if they're estimable, then it has to be a treatment contrast. And notice we take a treatment contrast that's estimable and we get it back, and it is estimable. Now let's load EM means. So it's the estimated marginal means, and it's a function that allows us to create treatment effects. So we're almost finished, so 3/4 of a page here. We're creating linear combinations, treatment effects specifically. So this is treatment 1 versus treatment 2. Now let's see if it's estimable. It is. Treatment 1 versus 3, it's estimable. And let's just go down the list. So this one is just the estimating the parameter for the covariant. This one here is another linear combination. Let's see if it's estimable, and it is because we get it back. Now the EM means, what we do is we take these L1, L2, and L3. Now we have to subset it because the parameters 2, 3, and 4 of this linear combination are associated with the machines or the treatment effects, the 3 parameters. And so and these are the estimates of it. Now to create the estimates by hand, we just take L times that beta parameter. And we also take the same linear combination times the second least squares estimate for beta. And they're the same. So no matter what least squares estimate we use, we get the same estimate. And notice here, so minus 104, minus 104, 1.58, 1.58, 2.62, 2.62. So we can do it from scratch or use this estimated marginal means. Now the variances associated with these, oh, it's not really coming across well on my screen, but if we watch the fourth video in the estimability, it shows you how to calculate the variance. So it's the square root of the mean squared error times a L times the generalized inverse of x transpose x, L, and that's like the variance. But we take the square root because in the estimated marginal means it provides the standard error. So notice here, so we have 1.01, 1.01, and then here we have 1.11, 1.11, 1.15, 1.15. So it's the same. So we calculate them by scratch or versus the built-in function. Okay, well, that's all I have for this video. Hopefully this illustration was informative. I'm going to try to remember and put the code in the comments. So if I don't, someone comment that they want it, and I'll absolutely copy and paste this code into the comments so you can copy it, paste it into your R program. Hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.